Hi everyone, I just wanted to do another electric potential and electric field problem. And our problem is as follows. A line charge of length 10 meters along the z-axis from z is equal to -5 to 5 meters has a linear charge density of lambda is equal to 2z, or the absolute value of z. And it's asking what is the electric potential and electric field intensity at 1, 0, 0 meters, or somewhere along this point. The first thing we all know that the electric potential equation is simply V is equal to KQ over R. But since we're looking at a line charge, we have to look at a little part of this, which we will call dz. And this dz will give off a dB. So instead, we will use this equation, dV is equal to K dQ over R. And if you're interested in 1, 0, 0, which will be this point right here, then this point will be R. Sorry. And then we will call this length X and this side Z, and then theta. Sorry, I didn't mean to draw it too long. So we also now know our R, but the question comes, and what is our dq? Well, dq will simply just be the charge density, lambda, which is given, times a little typical element, dz. So, plugging in what we now know that dV is equal to K dQ, which is lambda dz over R. Now, let's plug in lambda, so we know that dV is now equal to K 2z over R dz. So now we can just take the integral of both sides. But what is our limits of integration in this case? Well, you could either do -5 to 5, or we can also do from 0 to 5. But if you choose to do the 0 to 5 method, you need to multiply it by 2, so you compensate for both sides, from 0 to 5 and 0 to -5. So in this case, so when you write that down, you can either do from -5 to 5, or 0 to 5 times 2, and the same integral. I will just choose this method today. So, if I choose this method, then the integral will now simply be V is equal to 4K lambda, integral from 0 to 5 of Z over R, after we take out the constants. And the constants again will just be 2 and K, and if I move it outside, will give us 4K. So let's plug in our R. So, and relate it back to the triangle. Our R will simply just be the square root of Z squared plus X squared. So V will be equal to 4K from 0 to 5, from Z over square root of z squared plus x squared dz. Oh, forgot the dz that was up here. So I simply just plugged in our r. So now you should know that this is just a u sub. So u sub, if you make u is equal to z squared plus x squared, then we're going to take the derivative of both sides. On the left hand side we take the derivative with respect to u, and on the right hand side we'll take it with respect to z, which will give us 2z dz. Now, figuring out what dz is, we'll get 1 over 2z du is then equal to dz. So, plugging in our u and replacing our dz, we will get v is now equal to 4k 0 to 5 z over square root of u and 1 over 2z du. Again, I simply replace a dz with 1 over 2z du. So, these z's will cancel out, and then the 2 can go on the outside. So we'll be left with 1 over 1 is equal to 4k divided by 2, which will then just be 2k integral from 0 to 5 of 1 over square root of u. And this will just be equal to 2k 0 to 5 of u to the negative 1/2 after we bring this to the numerator. And now this is just a simple integral, and we will just get v is equal to 2k, and if you take the integral of this, we'll get divided by 1/2, and then it will be u to 1/2 from 0 to 5. But we can't simply just plug in 0 to 5. We have to plug in a u back in, which is z squared plus x squared. So it will just be v is now equal to 4k after we divide it by 1/2. So it will be the square root of z squared plus x squared, because the power of 1/2 is simply the square root, from 0 to 5. And we simply now plug in our numbers. So, plugging in our 5, we will get that v is then equal to 4k, and we plug in 5, we'll get 5 squared plus x squared square root minus, plugging in the 0 now, 0 squared plus x squared. And again, this is simply from plugging in our 5 and 0 into z. So now v would then just be equal to 4k 25, 5 squared is 25, plus x squared minus square root of x squared. And square root of x squared is simply x. So we can just write v is then equal to 4k 25 plus x squared minus x. So now, to do the second part of the problem, since we already have the electric potential, Now we need to find the electric field intensity at 100 meters. So you can either use the formula to get the electric field, which is just kq over r squared, or we can also just take the gradient of our electric potential, which will give us the electric field intensity. I will do the gradient method today, and the benefit of doing the gradient method is you don't have to worry about the direction. You can let the voltage, the electric potential worry about the direction for you, because you know that the electric field is equal to negative gradient of V. And you should remember what the gradient is. It's simply, if I put a negative outside, it will be x partial derivative of x plus y hat partial derivative of y plus z hat and a partial derivative of z. And it will be V, or the electric potential, 4k square root of 25 plus x squared minus x. So if you look at our electric potential, you should realize that we don't have any y or z components. That means we don't have to do these, for the y, or do the z. All we really have to do is the negative x hat 4k square root of 25 plus x squared minus x. So all we have to do is take the partial derivative with respect to x of our electric potential. So now, solving for this partial derivative, I can write this as E is also equal to negative x hat partial derivative of x 4k 25 plus x squared 2 to 1/2 minus x. And it will make it easier to do the derivative. So, taking the partial derivative with respect to x will simply give us E is equal to negative 4k times 1/2, after we take the derivative of the 25 plus x squared, 25 plus x squared to 1/2, and then we have to worry about chain rule, so we get 2x on the outside, and then minus 1 after taking the derivative of x. And don't forget the x hat direction. And the x hat came from taking the gradient, and this came from taking the derivative of 25 plus x squared to the 1/2. Again, this is negative 1/2. Again, this is just simply from minusing 1 from 1/2 and bringing it down, and then taking the chain rule of x squared, which is 2x. So just to make this a little bit nicer, we get E is now equal to negative 4k of x over, if I bring this to the denominator, it will be the square root of 25 plus x squared minus 1. And the reason why we only have x on the numerator is because the 2's cancel out, and we get x on the numerator. And don't forget the direction, x hat. So now this will just be our electric potential, electric field. And then we also have our electric potential. So now, we also now need to find the electric potential and electric field intensity at 100 meters. So now we can just simply plug in it using our electric potential and electric field intensity equations. So starting with our electric potential, you know that V of 1 is equal to 4K the square root of 25 plus x squared, but we can just plug in 1 because we know that our electric field and electric potential only care about the x direction. So this will be x squared, or 1 squared minus x, which will just be 1. And plugging into the calculator, you will get 16.4 Coulomb's constant. And Coulomb's constant is simply 8.99 times 10 to the 9. And we will get 148 gigawatts. And then the same method can be used for the electric field intensity, which will just be E of 1, and we simply just have to plug in 1 into our equation, which will give us 4K, 1, which 1 right here, minus 1 if you plug in x is equal to 1, over 25 plus 1 squared, plugging in 1 into our x. But this time, remember to put the direction, because E field has direction, follow the vector sign. And then you will get E of 1 is simply equal to 3.22 kx hat. And plugging in our k, you'll get 28.9 x hat direction gigawatts per meter. And this will be the final answer.